Hi, everyone. So my name is Bill. When I started this ZK Apps Builder program, I was thinking on the lines of trying to do something useful about what types of MEV are possible on Mina. Just because my background is I really like researching these sorts of topics. And that's what I'd say the first half of the Builders program was spent working on, is profiling MEV on Mina. But then the second half of the program shifted more towards this proof of exploit idea as I was wrapping up my findings on MEV. And so I'll share progress on both of those today. So part one is followed a timeline roughly like I began by researching sort of the inner workings of current Mina protocol at the consensus layer, and also the upcoming ZK apps and what it would change about consensus. Here I was trying to identify forms of MEV present on Mina compared to other L1s like Bitcoin, Ethereum, stuff like that. And the final product, originally I thought the final product would be something like a ZK app that helps monitor MEV levels or something like that. But I realized that it was a little bit too early at the moment for there to be, I guess, a use for monitoring MEV, given that ZK apps are still very early. So I thought more useful would be like a 3-part series explaining my findings, such that it could be helpful for guiding future developers. This is intended for like general readers, not just ones who are already familiar with Mina, just because I recognize that there's a potential that this could reach more people that way. And parts 1, 2, and 3 are ready as drafts. I've shared them with a couple of people, including Gina and Jack, and Brandon, who's more like an architect for Mina, for review. But I also would love any of the feedback that any of y'all can give for those parts. So here I'm going to summarize sort of what the 3 parts of that series are describing. And the first part is a basic overview of Mina's anatomy from the consensus view. And the image on the right is taken from the economic white paper from Mina. And I think about it in my mind as sort of Bitcoin, but secured by proof of stake instead, as a starting point. And then you see I have a bunch of these plus signs. And these plus signs are like innovations that I think of that Mina has added onto this basic premise. In particular, Mina has, first, of course, snarks being part of that process, where transactions should be compiled into snarks. Actually, I can turn on the laser pointer. That's better. Okay, transactions can be compiled into snarks. And there's a marketplace of snark workers that is responsible for doing this compilation. And they're competing to get paid for each of these. So you see that there's like an order book of snarks that you can select from, and the snark workers are going to try to offer you the lowest fee to compile your snarks. And block producers, or BPs, they have to buy snarks for transactions from these snark producers. So that's how the snark workers make money, is they take the money from the block producers. These block producers, however, aren't just like buying snarks for their block. They have to buy snarks for the transactions in a previous block. And so you can see in this red circle, that's where this first class of snarks is sort of introduced in the consensus. Of course, I'm going a little bit faster here than if like you were somebody not familiar with Mina, but I'm just summarizing sort of the way I'm viewing like what makes Mina different, eventually useful for profiling what MEV is possible on Mina. So this class of snarks, I'll always denote in red for the rest of the slides. And each of these snarks, their goal is just to check that their specific transaction is valid. So things like that the money wasn't double spent, that the person trying to spend it actually has that money, things like that. Then as we follow this timeline further, we encounter a second type of snark, which is once the block producer has received snarks from these snark workers, it has to combine each of these transaction snarks, which were red, into a larger snark, which is blue. And this snark is eventually going to become the new head of the blockchain. But this snark is also going to have another important task, which is it's going to need to check the validity of the previous snark, which was the head of the blockchain. And this is what makes a snark a recursive one. This is what Mina likes to talk about a lot, with like pickles and kimchi being very good for producing recursive snarks as opposed to other proving systems. This is very important because it means that at the end of the day, Mina's blockchain is secured by one very large recursive snark, and that is much better for keeping the size of the blockchain constant, as Mina likes to talk about. And so I circled this part in blue at the bottom of this timeline. And so these innovations built on top of this like Bitcoin plus proof of stake based layer is how I imagine like current Mina protocol working. The caveat here is, of course, most of this knowledge is derived from talking to people like Brandon. So there might be mistakes, and again, like the drafts are very, very open to feedback. But this is the understanding of how Mina works today. Second part is how does Mina work once these ZK apps are introduced? And for this, I think about ZK apps as smart contracts on Mina that compile into ZK snarks. This is in contrast to, say, smart contracts on like Ethereum that compile into like EVM bytecode. And that's where sort of the similarities stop, because there's a lot of innovations that ZK apps bring with them. Namely, first, that like the smart contract logic of a ZK app is not hosted on-chain. It's hosted somewhere off-chain. And for people like me who are used to thinking about ZK apps from like a Groth16 point of view, I like to think of the smart contract logic as the circuit, or C, in this like depiction of like how the Groth16 proving system sort of works, as the circuit C that is part of the snark system. Then the blockchain, what does the blockchain have on it? The blockchain will host the verifier of this circuit at a specific address. And the verifier from the Groth16 proving system is the party trying to receive a proof and then decide whether it is valid or invalid. Of course, this is not the exact way that it works on Mina, but this is, I guess, a good way to think about it from first principles if you're not as familiar with Mina yet. Then the user, or the client, will act as the prover in this proving system. And the prover's responsibility is to generate a proof, in this case, a zero-knowledge snark proof, that it has interacted with the smart contract or the circuit correctly. And so that proof will then get sent to the verifier, and the verifier will choose to accept or reject it. So unlike another L1, where the smart contracts are going to execute the code on Mina, there is no execution of the code on chain. Rather, it is a verification that the execution, which sort of happens off chain, was done correctly. And so that's correct here means things like, you know, I'm a user and this is the account balance that corresponds to mine, and I'm like withdrawing money that I had deposited before and I haven't withdrawn it before, checks like that. And so this, notice, is a new type of snark, so I've denoted it in green. So now we have 3 types of snarks that are part of our Mina protocol once ZK apps go live. And all 3 of these snarks are innovations upon like what other blockchains have at the moment. A very important question here that I needed to answer for determining what sorts of MEV are possible is what exactly is private in this ZK app Mina world? And the answers I arrived at were, well, there's 3 main types of data here. There's persistent memory, which is like on-chain state, and that is not private in the sense that nodes will record this sort of on-chain state in its raw form. Last week, when we had that presentation about the proving systems, I learned that, like, yeah, it's true. If you wanted to keep this part of your ZK app private, you could choose to store cryptographic commitments of your on-chain state instead of the raw on-chain state, and that way you can introduce some level of privacy. But by default, this is intended to be shared by the network, this sort of persistent on-chain memory. The second class of data is input data to your ZK apps. Think about this as like the arguments that you pass into your functions. This part is private. The reason it is private is because you as a user can choose to place it into the private witness part of your proof. And when it is inside the private witness part, it's protected by the zero-knowledge nature of the snarks. As a result, it's not going to be revealed to anybody on-chain what exact inputs you sent to the ZK app. However, do keep in mind that the resulting changes to on-chain state are going to be public, so it could still give away something about the fact that you even interacted with the ZK app. That could be information that you can't protect other people from seeing, but at least you can protect the nature of that input data. And the final class of data is the source code of these ZK apps, and that is also, I guess, by default private in the sense that it's not hosted on the chain. You can send it to the users of your ZK app, but you don't have to send it to everybody. And the users who do not have your smart contract source code cannot really interact with it. In that sense, it is private. But of course, it is not private. It's not like guaranteed to always be private because users of a ZK app could share it with anybody, publish it on the web, do whatever they want with it. But thinking about this in terms of like the different levels of privacy for different parts of Mina's ZK app data is useful for finally getting to part 3, which is what forms of MEV are available on Mina compared to other blockchains. And so there's 2 tables, one on this slide and one on the next slide, that summarize the findings here. The first slide is talking about what sorts of MEV exist on current Mina, so what current Mina has in terms of MEV versus what current Mina does not have, versus what the baseline, like Bitcoin plus proof of stake, would have, and what Bitcoin plus proof of stake would not have. So each of these quadrants represents some combination of these. So let's start with the top left quadrant. And obviously, for purpose of MEV, we'd rather have less MEV than more MEV, just because MEV is usually a bit unhealthy for the ecosystem. So we want more things to be in these columns rather than these columns. And in particular, if we can have things in this box, this quadrant right here, that would be really good. But first, to compare current Mina versus Bitcoin proof of stake, we see that both of them share certain types of MEV, namely block reorganizations. Block reorgs are a very basic form of MEV where if you are a block producer and you choose to build on top of the previous consensus winner block, then everything is nice and happy. But if you happen to want to build on top of a different consensus winner, maybe because the network got partitioned at some point and your new block happens to be the one that people continue to build on, then the previous consensus winner might become orphan meaning that no one continues to build on top of it, and as a result, it becomes an illegitimate branch of the blockchain. And in that case, you have reorganized the blockchain from that consensus winner to your consensus winner, and the transactions on that block, while at some point in time might have seemed final or seemed like they were going to be built on top of, now they become effectively voided. And in that sense, you as a block producer could be extracting value because maybe the transactions that you prefer have gone into this new consensus winner, whereas the old consensus winner had transactions you didn't really like, and so you've successfully excluded them. Block reorgs are possible on Bitcoin and Mina, as long as you're using some sort of Byzantine consensus mechanism like proof of stake or whatnot. It can happen as long as you have a longest chain lens mentality. Another form of MEV that both of them share is transaction reordering, which is you as a block producer, you are an entity that can have authority in sequencing transactions in your block. So you can choose which transactions go first, which transactions go second. And thus, if you have maybe two transactions where only one of the two could ever go through, for instance, if both transactions are trying to send money from the same address, but the address only has one Mina worth of tokens in it, then whichever transaction gets put first will be the one that works, and that's the one that comes second will not go through. And so if you're the block producer, maybe you prefer one of those two above the other. Say one of the two transactions pays you and the other transaction pays someone else, then you want yours to go first. And so that's an example of an MEV that you can do on both Bitcoin and Bitcoin proof of stake and Mina. Then let's talk about what current Mina has that Bitcoin proof of stake does not have to deal with. And these both come from the innovation of using snarks and snark workers. The first one is because you have a snark marketplace with a bunch of snark workers, if those snark workers were to monopolize or unionize or whatever, then they can cause a denial of service attack, or basically like a strike, right? If nobody wants to compile snarks, then your chain effectively halts to stand still. Of course, there's a mechanism in place that says that if there are fewer snark workers, then the price that a snark worker could charge for their snark is going to go up, right? So it's not going to be a denial of service attack that lasts forever, because at some point, the economic incentive to comply and to build a snark outweighs the incentive to stay part of this denial of service attack, but it can cause the blockchain to become congested. And if the snark workers are successfully monopolized, then they can effectively charge more for their snarks than the fair market value. And so in this way, the snark workers can extract MEV from the system. Another peculiarity in terms of MEV that Mina has is, for instance, if currently snark work is expensive, say that the next transaction that a block producer has to pay to produce a snark for is going to be really, really expensive, the block producer can sometimes have an incentive to just not completely fill their block with transactions. If they choose to not add an additional transaction to their block, they'll have to pay for one fewer snark to be built for a previous transaction. And if that snark that has to be built is really expensive, economically, it might just make sense for them to not include as many transactions as they could. And this is another form of MEV because, in this case, the block producer is doing something that tries to maximize its own value, but this is at the expense of including more transactions in our blockchain. Finally, we have forms of MEV that Mina and Bitcoin/proof of stake do not have to deal with, which is mainly smart contract MEV. This is the more complex forms of MEV that require basically smart contract environments to exist. Since both of them are sort of payment-based networks at the moment, they don't have to deal with that. Once we get to ZK app Mina, that all goes out the window. In particular, ZK app Mina and Ethereum both have this sort of smart contract way of thinking about the world. So they are both much more susceptible to MEV. And so I think ZK app Mina has a very fair point of comparison in Ethereum. So here the table is between ZK app Mina and Ethereum as opposed to Bitcoin proof of stake. Ethereum and ZK app Mina both have certain forms of MEV such as front-running and back-running attacks if the source code is known to whoever's trying to attack that ZK app. If the source code is known, the ZK app attacker can try to back-run certain transactions to be first in line for them. front run and then back run certain transactions in order to increase the cost for whoever's transaction is going through, which is called the sandwich attack. There are also other forms of MEV that, if the source code is known, then like Ethereum would have to deal with, that Mina doesn't have to. So in particular, like because the source code on Mina is not by default completely public to everybody, if you don't happen to know the source code for a certain ZK app, you can't do certain types of MEV that you could do on Ethereum. So that's why this quadrant now has content, whereas on the previous slide it didn't, which is to say, if you don't know what the source code is for a ZK app, you can't do front-running and back-running attacks. And you can't do generalized front-running attacks. Generalized front-running attacks are ones where you try to duplicate some other user's transaction to see if it would make money if you were to run it yourself. And if it does, that you put your transaction right in front of that user's, which is front-running them, such that you will successfully monetize that opportunity. And then once it gets to that user's chance, the opportunity is gone. That's not possible if you don't know the source code, because then you just can't really interact with that ZK app. And that, as a result, is one way where the privacy of ZK apps can protect users on Mina. And also the fact that inputs on ZK apps are also private helps reduce the chance that generalized front running could succeed even if you knew the source code, because in that case, you don't know what inputs the original user was giving the smart contract in order to trigger that desirable output. But there is finally one form of MEV that ZK app Mina does have that Ethereum does not have to deal with. And that is the fact that since the source code starts as private, it is possible to censor certain groups of people from using your smart contract by just not sharing the source code with them. And this can be viewed as a form of MEV if it is used strategically to improve the profit mechanisms for a certain party, block producers or other users. Say, if you want to just not have as much competition on the smart contract and just share the code with a certain set of users, then you can effectively increase the amount of monetization opportunities for yourself. That's a summary of the findings that I compiled in the first half of this program. And there was further work that I thought about, which could include building a dashboard to monitor MEV on the current Mina, which is the payment system Mina, such as block reorgs. But more importantly, what I was thinking about was to try to build a dashboard that monitors more complex forms of smart contract MEV. And unfortunately, that's just something that right now, since ZK apps are still early, wouldn't have too much of a use case for. But once ZK apps do go live on mainnet, and once there is more activity and more primitives built on there, then a dashboard like that would be very important for monitoring just what sorts of MEV are present. And in the long run, it would be very valuable to have sort of a leaderboard that compares how resistant certain L1s are to MEV. And I think this is a great point of comparison, especially for developers that are choosing between which blockchains to develop on. And you could say that, current MEV, if we looked at that, current Mina, if we looked at that table comparing it to Bitcoin, might not be as MEV resistant, but ZK app Mina, because of the privacy guarantees of ZK apps, would be more MEV resistant than Ethereum. And that sort of leaderboard could be very useful to developers or newcomers. At this point, I'll pause just for some questions before I go to the second half of the program. Okay, then I'll continue to what I worked on for the second half, or I guess the last 3 or 4 weeks, which is this proof of exploit idea for Mina ZK app. In particular, the use case here is there are a lot of smart contracts that are going to be developed on Mina, as well as other L1s, and identifying exploits in those smart contracts is very important for developers. You need to catch the bugs in order and then fix them, and you'd rather find out that the bugs exist than just pretend that they're never found. But existing mechanisms for identifying exploits in smart contracts all have their own sort of issues. And so here's a table of the combinations of different mechanisms for finding exploits in in the status quo. So there's 2 choices when you're looking for mechanisms for finding exploits. There's centralized mechanisms and there's decentralized mechanisms. And then on the other hand, there's methods where you have to execute the exploit itself in order to show that it exists, or you have a way to prove that the exploit exists without having to execute it. And so in the quadrant where you have a centralized mechanism to execute exploits, you might imagine something like a private testnet that is controlled by whichever team is behind a protocol. They launch a private testnet. It's centralized in the sense that this team controls the testnet, but people can go in there and just try to hack the smart contract and then cause an exploit to occur in that private testnet. And that way you're actually trying to execute an exploit. Over here, you can think about centralized solutions that allow you to not execute an exploit, but just demonstrate a proof of an exploit, such as most bug bounty programs, like those hosted by MEV. These bug bounty programs are ones where they put out an objective, which is like, find something wrong with this contract. And then when you believe you found something wrong, you don't go into the testnet or the mainnet and actually cause the exploit to occur, but rather you submit a submission for the bug bounty. And it's centralized in the sense that there is somebody judging whether this is a valid submission or not. There's like a human there, and they judge whether this is actual proof of exploit. And if it is, then you collect some money. But if they decide it isn't, then like you're out of luck. Then in this quadrant down here, there are decentralized solutions, which are obviously a bit more preferable because it doesn't require some element of trust or some other human to be in the loop. Unfortunately, at the moment, there are no decentralized solutions that just require you to prove that an exploit can be possible. Decentralized solutions right now require you to actually execute that exploit. And so there's two main routes you could use to create mechanisms for this. One is to actually just put on your black hat and go and hack it, and then just execute the exploit, steal all the money, that sort of thing. Obviously, frowned upon. Another interesting avenue is there are products like anti-tests, which are basically decentralized pots of tokens, which if you successfully execute an exploit, those smart contracts will pay out their tokens as a way of rewarding that you have found an exploit. Both of these require you to actually go and execute that exploit. And we'd rather, of course, just prove that the exploit exists without having to actually damage the system that we're working with. And so that's where the last quadrant comes in. If we want a decentralized mechanism that just requires us to prove that exploits exist without having to execute them, then the only way is to use ZK snarks. We want to create ZK proofs that these exploits can occur based on our knowledge, such that we can claim bug bounties and such in a decentralized way. And Mina ZK apps are a good environment for building these. To think about what exactly it means to execute an exploit and what the difference between executing an exploit versus proving that an exploit can occur, I first paint out the logic path timeline for executing an exploit. The first step is obviously find a smart contract with an exploit in it. The second step is to determine what transactions you need to send to this smart contract, what inputs do you need to send in those transactions in order to trigger that exploit. Third step is straightforward. Execute the transactions, trigger the exploit. And the fourth step is claim that price. So whether it's that bug bounty program's loot or it is the actual token reserves that you have stored there. The modifications, if you're trying to prove that an exploit exists, are in steps 3 and 4. In step 3, instead of executing those transactions to trigger the exploit, you just create a ZK snark proving that those transactions and inputs together will trigger the exploit. And then in step 4, you can claim the price by submitting the ZK snark to a verifier. And that smart contract verifier maybe hosts a bug bounty in it. And then when you submit the ZK snark and the verifier checks that it's correct, it'll pay out that bounty to you. With this sort of logic in mind, I thought through for the past 2 weeks or so the feasibility of this sort of application, this sort of decentralized bug bounty application. And the findings are, well, for other chains, namely Ethereum, that's where I spend the most time thinking, these generalized ZK snarks that prove exploits are possible, they're not really feasible yet from a technological perspective, mainly because they require you to be able to build ZK snarks for basically arbitrary EVM bytecode execution. You basically have to be able to prove that any sort of set of instructions sent to the EVM is valid. And that's something that is just not technologically feasible yet. It's actively being researched by lots of L2 projects and lots of very smart people on Ethereum. But on Mina Protocol, it could be a different story. And this is where I don't yet have a complete picture, but I plan to continue to work through and talk to people like Gregor from the Mina Foundation and stuff, as to understand for Mina Protocol, because you already have ZK apps that build ZK snarks of smart contract execution on those apps, you already have a proving system that is more friendly than the EVM. And using Snarky and Pickles, you can potentially cross this gap that these EVM-centered ZK snark projects aren't able to cross yet. And so there is a potential that this sort of application could be possible on Mina, where it's not possible elsewhere yet. A very simple example to just motivate people thinking about this proof of exploit concept. This is an example that I was able to build on Ethereum but should probably be even easier to build on Mina. This simple example of a proof of exploit is to prove knowledge of a private key to a multi-sig. Lots of things in the crypto ecosystem are secured by multi-sigs. Like lots of bridges are secured by multi-sigs. Some wallets are secured by multi-sig. Multi-signature is just like a A over B, like threshold for how many signatures out of a pool need to sign a certain thing in order for it to be deemed valid. And if you know the private key to one of these signers when you shouldn't, then that is a pretty big exploit. And so if you can prove that knowledge without giving up the private key, that's something that's very valuable. And that's something that is going to require ZK Snark circuits. I built it using Circom and Snarky.js. Sorry, not Snarky.js, Snark.js. I built it using those because there's a helpful library there called Circom ECDSA for building this sort of ZK Snark. But I'm trying now to build it, basically the equivalent of it on Mina with ZK apps. And so that's sort of where we end up today. And moving forward, I'm going to continue exploring this direction and think about how you could potentially create a useful application for Mina and potentially new use case for Mina as a way to prove exploits could occur on other smart contract systems using Mina's unique snark-based proving systems. So that's the end of the presentation. I know I went over time, but thankfully there's only 2 of us today. And I will stop sharing and leave myself open to questions.